Hello and welcome back to The Visual Dynamics of Upper Paleolithic Art. I'm Julia, and today we're going to unravel how neuroscience has helped us understand the mysterious connection between ancient animal depictions and the very origins of writing. Now, if you've been following along, you'll remember in previous episodes we talked about how our brains are wired to see animals in ambiguous shapes, what we called hyperimagery and pareidolia. But today we're going to dig even deeper into what's actually happening in the brain when we look at these ancient images. So here's something that absolutely fascinated me when I first read about it. Neuroimaging studies have shown that when you look at a real animal, and when you look at just the outline of that animal, especially in profile, sideways on, the same areas of your visual cortex light up. It's like your brain doesn't really care if it's a living, breathing bison or just a few lines on a cave wall. As long as the outline is there, your brain fills in the rest. This is especially true when the animal is shown in that classic sideways view, with all the important features visible. It's a kind of cognitive economy. The brain is all about efficiency, and prehistoric artists seem to know this intuitively. They'd often leave parts of the outline unfinished, almost inviting your brain to complete the picture. It's a bit like those puzzles where you only need a few clues to guess the answer. I've always been a bit obsessed with those geometric marks you see alongside the animals, zigzags, crosshatches, little clusters of lines. Turns out making these marks wasn't just doodling. Studies show that drawing animals and these geometric patterns actually sharpened the neural networks in the visual cortex. The more you practiced, the better your brain got at both making and recognizing lines. There's even evidence that people got a kind of pleasure from making these patterns, a sort of neural fluency, because the brain just loves processing simple, efficient shapes. And, funnily enough, geometric motifs actually outnumber animal depictions in some Upper Paleolithic sites, and they go back even further in time. So drawing wasn't just about art, it was training the brain for both visual recognition and, as we'll see, the first steps toward communication. Now, let's follow that thread from simple outlines to the birth of writing. If you look at the earliest scripts, Egyptian hieroglyphs, cuneiform, even early alphabets, they're all built from the same basic ingredients: lines, junctions, angles, and schematic motifs. There's a reason for that. The visual cortex is especially sensitive to these features, and they're easy for the brain to recognize and reproduce. In fact, research shows that all writing systems, ancient and modern, rely on a handful of these basic shapes: T-junctions, L-shapes, X's, because they're the most common features in the natural world and the easiest for our brains to process. Here's where it gets really interesting. As societies grew more complex, the brain's object recognition areas, especially something called the visual word form area, or VWFA, got recycled for reading and writing. This is what neuroscientist Stanislas Dehaene calls neuronal recycling. The same brain regions that once helped us spot a camouflaged animal in the bushes started to help us recognize written symbols. And this wasn't just a straight line from pictures to words. It was a messy, back-and-forth process with lots of trial and error, standardization, and even regression. There's a brilliant case study from Egypt that really brings this to life. Archaeologists have found over 160 naturalistic animal outlines engraved on rocks near the Nile, some dating back 15,000 years. If you look at Figure 7 on page 15 of Hodgson's article, you'll see these beautiful sideways profiles of bovids, cattle basically, etched into the stone. Over thousands of years, these images became more and more schematic, eventually morphing into the first hieroglyphs. Darnell's discoveries in the eastern desert show how these rock engravings of animals, bulls, giraffes, storks, were the direct precursors to the hieroglyphic script, It's a perfect example of how the brain's visual preferences, shaped by evolution, set the stage for the invention of writing as societies needed new ways to store and transmit information. So, what actually happens in the brain when we move from pictures to true writing? This is where things get a bit technical, but stick with me. Brain imaging studies show that pictorial, numerical, and phonetic systems each use different neural pathways. For example, numeracy, the ability to process numbers, relies on the number form area, or NFA, which is mostly in the right hemisphere. Writing and reading, on the other hand, depend on the VWFA in the left hemisphere. If you look at figures 9 and 10 of Hodgson's 2024 paper, you'll see these networks mapped out. People with damage to the VWFA can't read or write, but they can still do maths and vice versa. So the brain keeps these systems pretty separate. But there's a twist. The transition from images to writing wasn't just about inventing new symbols. It involved something called schematic iconicity, where a picture is pared down to its most essential features, and the rebus principle, where a symbol stands for a sound or a word, not just an object. This is how cuneiform, for example, bridged the gap between imagery and language. Overman's research shows that these feedback mechanisms, where the brain gets better at recognizing and producing marks, helped refine early scripts into true alphabets. And here's a fun fact that always makes me smile. You know how kids often mix up B and D or P and Q when they're learning to read? That's because of something called mirror invariance. The visual cortex is used to recognizing objects from any angle, so a bison facing left or right is still a bison. But with letters, direction suddenly matters, and the brain has to unlearn that old habit. Dehaney and Pagado's studies show that with enough practice, the brain rewires itself to tell these shapes apart. But it's a real challenge at first. It's a lovely example of how our ancient visual instincts still shape the way we learn to read and write today. So, to wrap up, what we see in the caves of Europe and the deserts of Egypt isn't just art. It's the story of how our brains, shaped by evolution and culture, laid the groundwork for writing. From unfinished animal outlines to the first alphabets, it's all part of the same journey. Thanks for joining me on this episode of the visual dynamics of Upper Paleolithic art. Next time we'll keep exploring how neuroscience and archaeology together can unlock even more secrets from our distant past. Until then, keep your eyes open for the patterns all around you.